Okay, let's pick up where we left off. Oops, let me get my iPad screen showing. So here is where we were, slightly cleaned up. And let's look at what this means. Okay, so we are going to need to model this in MATLAB. So we want to make sure that we keep track of things, and I highly recommend that you write what's on the screen right now on a scrap sheet of paper that you can refer to as we write our code. Because these equations are what we are going to code in. So let me remind you, okay, let's just go from left to right. So to get from the S pole into the E pole, people are leaving S and going into E. AIS determines that rate. So equation 1 is that ds dt, the negative sign means we're losing a population at a rate of AIS. All right. Now dt, then when you look at E, it's between AIS flowing in and BE flowing out. So equation 2 is that DE, that's an E right there, DE dt, let me make my E clear, DE dt is AIS minus BE. Then we get over here when you're at I, you have BE flowing in and CI flowing out. So equation 3 is that DI dt is BE minus CI. And then finally, equation 4, things only flow into the removed pole. We're going to assume that no one gets who has been removed will go back into being the susceptible. Right now, it seems like that's the case for the COVID-19. There was some initial data that seemed to indicate otherwise, but we won't be flowing back over into the susceptible pool. So once you're removed, you're always removed, hopefully not by death, but we'll talk more about that in a future version. Now, remember equation 1, we could transform. We don't need to use 4 differential equations because the condition S plus E plus I plus R, when you add them all up, that's everybody. So we're going to use that S is equal to 1 minus E minus I minus R. So this is what we will put in instead of equation 1. So we'll see that showing up in the code. So make sure you can take a screenshot of this, or you can print it out, or copy it over. It's actually not a bad exercise to pause the video and take just a couple of minutes to copy down the model. That is what we're going to program into MATLAB. So let me pause the video and switch to MATLAB. Okay, so here we are in MATLAB with the last code that we wrote. Make sure you're working with this code because we're going to revise it again. We're going to add the E, but as always, I didn't do this very well in a previous video. We should rename it before we change it because as soon as I start changing things, they will go into the code that I've already saved as the SEIR with vaccine model. So we are going to update that. So let's rename it right away. So let me go to Save As. Hold on a moment. Well, I'm not sure. I'm having a little trouble with the Save As button. Let me pause my video and work this out. Okay, I believe that my problem was simply that my MATLAB was still booting up, so it wasn't ready to do Save As. So now I'm going to save this. We are adding an E to the model name. So if you just click your mouse into the title and add an E to everything that we already have, we can save that. And I should save that same thing right up here in the opening line of the code. Okay, so we've added the state variable E, so my opening comment should do that. Okay, and then look at the parameters that we have. Okay, I want you to set all of your parameters to be equal to this so that we all have the same starting point. So pause the video and set your parameters to match what I have. All right, so hopefully you have done that. Now, if we run this is sort of modeling one of the problems we had in one of the videos where A was 2 and B was 1/2. We're going to stick with those things. Notice DV equals 0, no vaccine. We're not going to work with a vaccine for now, but we'll leave it in the model so that you can use it later. But as long as DV is 0, no vaccines are being distributed. So that was something you can work with later. We're looking at 1 year worth of data, and let's keep on going with this. All right, so 1% of the population is pretty high. So what I want to do is, in New Jersey, when all of this started, it was definitely not 1% of the population. Let's make it 0.1%. And if you run this, you can see it pushed, the peak ended up being at this, coming up to the same point. All it did is it pushed it out further in time because it takes a couple of weeks for the 0.1% of the population to reach 1%. Then it grows just pretty much the way we had expected from before. Let's make that 0.01% of the population. So if you're talking about 9 million people, that's 9e⁶. If you take, that would still be 900 people that would be infected. Maybe we should add one more 0. So it's probably more like 9 people. So this is, in fact, with that many zeros, let's just call it 1e⁻⁵. All right, so that gets us down to about 9 people starting this out. And you can see that only bought us a couple of weeks. It pushed the peak back. We stayed pretty flat for a couple of weeks, but because of that exponential growth factor at the beginning, it just took a little more time before we suddenly shot up again. And the peak of I is at about the same place. So that's kind of interesting. Starting with the initial amount we start with simply buys a couple of extra weeks to react, but that's where we are. All right, so we have an A value of 2, and let's keep making our model. Now, you're aware in this new model, the first thing we have to do is introduce a C value. So we have an A, B, and a C. Now the C is going to take the place of the old B. So I'm going to make that 0.5. And we're going to keep the B value also at 0.5. Now let's rename these coefficients because we have A, B, and C. Oh, I better not highlight all of that. Our first coefficient, let me put a tab here. We're just going to call this the S to E coefficient. Okay, and the units are per week in our model. When you look at an article, shortly the time frame will be days, but they'll be talking about 20 and 30 days at a time to see what happens. So we'll have the S to E coefficient. B is going to be the E to I coefficient, and that's per week, so weeks to the -1. And then C will be our coefficient that takes us from I to R coefficient. So we have the complete train of coefficients lined up. Pause if you get behind in your typing, but we now can go from S to E, E to I, and I to R with those 3 coefficients. There's not much that we have to do to the code. Okay, we still will keep no vaccine. The time delay doesn't matter if we don't have vaccine. Then T max will do a year for now, unless we need to change it otherwise. The time steps, we can make those as big or small as we want. That just, our graph seems smooth enough with that time step, so we'll keep it. It doesn't take long to plot it. I max just gives us a little, the 1.1 gives us a little buffer at the top of the graph so that we don't run along the top. And right now we have we have plot choices 1, 2, 3, and 4. It looks like though this gives us S, I, or R, or all of them at once. So we obviously want to bump these back. So 2 needs to be E, 3 needs to be I, 4 needs to be R because we have the SEIR model, and 5 will equal all. Okay, so let's change our plot choice to 5 for now. We'll do all of them. We'll need to make sure that plot choice 2 is going to be available. So we're going to add that into the code as we go down. Let's just linearly go down the code and see if there's anything we need to change. The time vectors should be the same. We're still doing 52 weeks. The length will be the same. We have an S, I, and R all zeroed out. I think you hopefully realize what we need to do here. We're going to have the SEIR model. So I need to add the E. Same thing, zeros, 1, comma, NT. If you want to copy one of them and paste it and edit it, that's fine. And this will be the exposed vector. Vector, not a typist. It might be nice actually to capitalize all of these because emphasize the S, E, I, and R. Oh, I already had R capitalized, so that's nice to have all of those. And then we need to set that initial I to start it off. If we don't do that, nothing will happen because no one's infected and no one will get infected. So that gets us to just leave this alone. We have an infection proportion already, so that will go into the code. The calculations, now this is the heart of the matter. This is where you want to be looking at your sheet of differential equations. And that flow diagram tells us what will happen. Okay. Now remember, for equation 1, we had S equals 1, representing 100%, minus, we were going to have EIR, so we already had minus I and R, so we simply have to add in, we'll do it in order, so I could put it anywhere, but I'm going to put it right in the front. Since it's the SEIR model, S will be 100% minus the other 3. So just make sure you get that line of code in, or the change to that line of code. All right. Now, these are going to change a lot. Okay, this is actually not too much. We just need to add a line of code for the E, and then some of the coefficients are going to change around. So let's keep going here. So we need a DE. Okay, now remember that's shorthand. I'm using that for DE dt. All right, and that will, remember, A flows in. So we have A times I. Looks a lot like what's on the line right below it. I probably could cut and paste, but I will do this. Make sure you're using capital letters for all of the state variables, S, E, I, and R. So DE, it has that flowing in, okay, to get the rate at which the exposed pool is growing, and then flowing out of it. Oh, so we have a minus sign, minus B times E IT. So originally we'll have no one exposed in the first time step, but then as the exposed numbers go up, we'll be taking that away from the exposed pool. So that line of code needed to be added. That matches our differential equation number 2. That gets us to, just pause if you need to catch up. That gets us to differential equation number 3. It's no longer given by this. What's flowing in to the infected group is B times E of IT. That was the BE flowing in. But we have C, that's lowercase c, by the way, times I of IT flowing out. So that matches our differential equation number 3. So make sure you fully update that. Lowercase b, lowercase c, capital E, capital I. So make sure you do that. And meanwhile, I'm going to comment this. This is the rate of change of exposed. And that'll be per week again. And so Just have that comment on there so our future selves will know what that is. All right. And now, oh, I need to add another line of code. You'll notice that each time I look at these 2 lines of code, after I found di dt, I needed to multiply it by dt to get how much I changes, and then add it on to the I that is already there, and that will give me the next I. So if I put those things together, that gave me the new I value. I never did that for E. So I need to add a line of code, bring that down, put my cursor back up. So I need to do almost the identical thing for E. So to get the next exposed value, I will take the current exposed value and add to it the DEDT, that should be capital E, times, let's see, what do we have here? Times DT. So this will give me the new exposed value. So we're just taking the rate of change times the time of the exposed, just like we did for the infected. Add that on to what was already there, and that will give us the next exposed value. So these equations will come in pairs. All right. Continuing onward, this was the block of code that was telling us how the R value was changing. And remember, this had to do with whether we had vaccine or not. All right. So if S of IT is greater than 0, and T of IT is greater than the delay. By the way, since DV is always 0, you'll notice that these 2 examples, DR is really the same thing no matter what. We're going to leave it in as it is so that we could have vaccine added later. But for now, this line of code, both lines of code for DR are equivalent to each other since DV is in fact equal to 0. So that gives us, then we can add the rate at which the removed pool is changing times dt. We add that onto the old one, and that's just the line of code that was already there. So let's just keep reading down and see if we need to change anything else. This was equation 1. We need to change that to have minus E of NT in there. The last E value, okay. And remember what that did after we finish, this is after the entire loop, because the loop only went up to N minus 1, NT minus 1. The last value of the susceptible population was still at 0. We needed to just reset the last susceptible value to not be 0. And that's important because if we're trying to pick off the minimum to figure out how low it went, it's important that the last value did not go to 0. So that's simply setting the last value outside of the loop so that everything will work out. Okay, then we get down to, this was the brains of the code. So once again, the differential equations are all showing up in here. So equations 1 through 4 are all showing up in this part of the code. So we can, actually, in fact, I don't want to annotate right now, but we can see that we have all 4 of those equations in this block of code. So this is a fairly small amount of code. It's only about 10 lines that completely model everything that we're doing with our differential equations. Now with our plots, we have an SIR and everything case. We obviously need to add a case for E. That means this I case will become case 3. Let's just change that a while. Our R case is case 4. And the everything case is case 5, but the everything case now is SEIR. So make sure you change this to SEIR in the comment, and that is case 5. we simply need to add case 2, and we're going to use green. Now, to add case 2, we can just modify case 1. So let me copy everything that was in case 1 rather than starting from scratch. Paste it in there. Let's back up the case 1 so it lines up nicely. And case 1 has become case 2. Now, right now, case 2 will do exactly the same thing as case 1. So let's figure out what changes we need to make so that case 2 will, in fact, plot E. We first of all want to change the comment. If we get down to line 55, we can see, we'll just line by line, we have an S in there. So the S clearly needs to become E. The axis can stay the same. So down to here, axis command can stay the same. We want to turn the grids on. That stays the same. The X label is still the time in weeks. The Y label and the title are two things we need to change. So just working our way down. This is the proportion that has been exposed. All right. And then the title would be proportion exposed versus time, which reminds me in the last graph, and so I'll just pause the video if you did need to catch up on case 2. But in case 5, the title probably does not have E in it. And that is correct. And also the legend does not have E. So these two things, oh, and the Y label. So these 3 lines of code have not been revised to have E. It's pretty easy to do that. So we simply have to put S, E, whoops, comma, I, and R. In fact, this label is going to get a little big, so let me take some of these spaces out. And then we have this title. And just to keep it from getting long, I'm actually going to remove a space there so it doesn't get much longer. And then for our legend, the first, you can see over here, right now we have S, I, and R. See where my mouse is. We want to definitely put E in the middle of this. So we want S, E, I, and R, and we'll keep the location the same. And I know there's one little thing that I forgot to do, but let's run the code and it'll show what I forgot to do. Okay, maybe I did something else. Extra legend entries. Okay, let me pause the video and see if I can figure out what caused that error, because it's not one I am familiar with immediately. So I'll pause it and explain what the error is. Okay, it's about 2 or 3 minutes later. I figured out the error. We have to change a couple of things. First, let's go back to case 2. All right. I won't show this mistake. If you look in case 1, you can see S was being plotted in blue. And right now, our expected values will also be plotted in blue. While this won't cause an error, it would be nice to change that to something like green. Okay. So that was one of the errors that it wouldn't cause a crash in the code, but we'll have blue lines for both of them. The bigger error, the reason that it crashed, it was saying there was an error in the legend, and the reason why was because I had 4 things in the legend, S, E, I, and R. So I was looking for 4 plots, and if we look at what we have in the code right now, we are only plotting S, I, and R, so it was confused because I was telling it in the legend to give me, to make the legend for apply to 4 things. So we need to put E in here. And we've already established that our color for that will be a green line. So that should now work. or so I believe. So let's try that. So the key thing, I needed to have all four SEINR plotted in order to have four things in the legend. So let me go back and run it and see if that in fact works. Yes, yes, good news, it worked. All right, so we can see our graph. And the expected line looks a little bit like the infected curve, except notice that it leads the infected curve because people who are, I'm sorry, I'm saying expected, E is for exposed. People will be exposed before they're fully infected and infectious, if you like. So the peak of the exposed curve precedes the peak of the infected curve. And as the exposed curve dies down, there are fewer and fewer people to feed into the infected pool. So those two curves look similar to each other. You can see because of the rate at which things are going in and out, the expected peak looks like it's a little bit higher. Let me just zoom in on that. The expected peak is a little bit higher than the infected peak because of the way things are flowing in and out. All right, but it seems to be working. We haven't tested case 2. Let's just make sure that if we only want to plot the expected, we can do that. So plot choice 2, run. And sure enough, yes, we have a beautiful curve for the expected in green. I'm sorry, I keep saying expected. Exposed, and you'll notice in my title, I spelled it exposed. So let's change that. So it's not doing exposed. That's kind of embarrassing. Let's change that to just exposed. So little spelling error. Those are the kinds of things you want to look at carefully before turning your own code in, so that it doesn't look silly. Okay, so let me pause for a moment. Okay, so we have a working model where we've added the exposed pool into all of the others. Let me go back to plotting all of them one last time. Let's see if this works. So that's choice 5 now. So if we run this, works very nicely. Remember, the A value is that key thing. So right now the A value is pretty high, meaning a lot of people are getting exposed, and we can see the exposed people become infected people. So let's lower that down to a 1 and see what happens. It should do what we expected. Oh my goodness, moving it out to 1, we can see that the epidemic actually gets pushed way out in time. So we're going to have to, let's look at that over 2 years. That would be 104 weeks. So that's good news. We're going to have it build up very slowly, which gives us a lot more time to react. And we can see that the peak becomes much lower. So good news, if we can bring that A value down to a 1, the peak of the infection peak, that's the primary thing we're concerned about. That's what swamps our medical system, has gotten much lower. It looks like the peak hits about a year later instead of when it was before. And look at the susceptible curves. The susceptible curve never goes below 0.2, and the infected curve never goes above 0.8. So it looks like 80% of the population did get infected eventually, but it bought us a year of time, and the crisis is going to be minimized. There's a chance we could have enough hospital beds to cover that. So this model showing what's going on. And once again, just if you zoom in on this region right here, it's easy to see the exposed pool just leads the infected pool by a little time. And it's just a little bit higher right now. Obviously can't be lower because you're going to have, you can't have more people become infected than were exposed. So this model seems to be working nicely. So let me stop this video. We're going to make one more big change to this code, but I'm going to do that in the next video.